All right, let's talk about a silent killer in RF systems, something that can absolutely destroy your signal, and you might not even know what's happening. We're diving into the polarization of radio waves, and we're using the fantastic technical report from the RFI detectives to guide us. And hey, just so you know, this is part 10 of our deep dive, a 20-part series. So if you're an RF tech or an engineer, this is exactly the kind of nitty-gritty detail that can make or break your entire system. Okay, let's just dive right in with a question for every RF pro out there. Are you silently losing signal? And I'm talking about a loss that doesn't set off any alarms, it just quietly eats away at your performance. So what are we talking about here? It's all about polarization. According to the RFI Detectives report, it's one of the settings you have the most control over, and, ironically, it's also one of the most forgotten. And I'm not kidding, getting this wrong is a huge deal. The losses aren't minor. They can be absolutely catastrophic to your link budget. Just imagine, you design a perfect system and then your signal just vanishes because of this one simple mismatch. So how do we deal with some of these tough RF challenges? Well, one of the most elegant tools in our toolbox is circular polarization. And it's not just another type of wave, it's a tool with some really unique powers. So what is it really? Well, think about a normal linear wave, right? It just oscillates up and down or side to side in one flat plane. Now, imagine that electric field isn't just bobbing up and down. It's actually spinning, drawing a perfect circle as it flies through the air. That, right there, is the essence of circular polarization. And the way it's created is actually pretty genius in its simplicity. You just take two regular old linear waves, stick them at 90 degrees to each other, shift one of them by 90 degrees in phase, and boom, they combine to create this beautiful rotating field. Okay, and this is where it gets really interesting. This unique spinning structure gives circular polarization. Well, I like to call it a magic trick. It's a truly amazing property that we can use to our advantage in system design. Here's the key takeaway, the big reveal. When a circularly polarized wave bounces off a building or the ground or pretty much any surface, it flips its spin. It's a fundamental behavior, and it is incredibly useful. And this slide just lays it all perfectly. Your transmitter sends out a right-hand circularly polarized signal. That's RHCP. The signal that comes straight to your antenna is received as RHCP. But look at that reflected signal. It bounces and flips to left-hand or LHCP. Now your antenna can easily tell them apart. It's brilliant. And that brings us right to its counterpart, left-hand circular polarization. As you just saw, LHCP isn't just some other flavor you can choose. It's the necessary functional partner to RHCP, and together they enable some of the most powerful tricks in RF engineering. You can see it right here in this table from the report. Take a look at LHCP. It's specifically described as being paired with RHCP. That pairing isn't just a small detail, it's the whole magic trick. It's the mechanism that lets us separate the signal we want from all the garbage reflections we don't. So what does this mean for us, the engineers in the field? Oh, the applications are huge. This is how your GPS receiver ignores all the signals bouncing off the ground and gets a clean lock on the satellite. It's how advanced radar systems filter out the noise and see the actual target. It even lets us cram more data into the same slice of spectrum by transmitting on both RHCP and LHCP at the same time. Okay, let's pull all this together. Why should you care about this on a Tuesday afternoon when you're trying to fix a system? Let's talk about the trade-offs and the big takeaway. All right, so what's the catch? Is there a downside? Well, here's the thing. The main disadvantage isn't really a flaw in LHCP itself. It's that the whole system, all that magic, depends on a perfect match. Its greatest strength, that ability to tell signals apart, becomes its biggest weakness if you get the setup wrong. And when I say it's bad to have a mismatch, I mean, how bad? Well, an antenna looking for LHCP is basically blind to an RHCP signal. The source material says this mismatch can give you a signal loss of 20 to 40 decibels. Just let that sink in for a second. That's not a weak signal. That's no signal. Game over. But let's end on the good news, because this is maybe the most powerful takeaway from the whole thing. Making sure your transmit and receive antennas have the right polarization is one of the only performance boosts you can get that costs absolutely nothing. No new hardware, no pricey upgrades. It's just checking a setting. It's free. So I'm going to leave you with this question. The next time a link is acting up, the next time you're troubleshooting a weak signal, before you start thinking about new gear or climbing a tower, have you checked what might be the simplest, most powerful, and most overlooked setting of all?